Hi, my name is Iván Cipiran. I am professor in the Department of Computer Science at the University of Chile. I am part of the organizer team of the SHREC 2021 track on retrieval of cultural heritage objects. Today, I am going to present the benchmark and results for our competition. There is a long story of contributions of computer graphics in the cultural heritage domain. The applications range from acquisition, reconstruction, and conservation of ancient objects to the development of complete systems for supporting archaeologists' labor. In all these applications, the data is a valuable resource to perform research and test the implemented tools before production. So we were motivated to contribute in this specific topic by building a benchmark of scanned 3D cultural heritage objects, which we make openly available to the research community. To build our dataset, we scanned objects from the Josefina Ramos de Cox Museum in Lima, Peru. We used a structured light scanner that provided high-resolution textured objects. We applied a post-processing method to clean the geometry. We also manually orient the objects so all of them lie on the XY plane. For the context, we simplified the model to approximately 40,000 triangles. Regarding the competition, we proposed two challenges: the Retrieval by Shape challenge and the Retrieval by Culture challenge. The former considers a classification according to the overall shape of the objects, and the dataset contains 938 models. On the other hand, the latter considers a classification according to the pre-Columbian culture that fabricated the object. This challenge is more difficult than the first one because the idea is to associate shape, style, and color information with a given culture. Note that in both challenges we split the data, 70% for training and 30% for testing. Also note that the class imbalance problem in both challenges even more evident in the Retrieval by Culture challenge. So we can say that our contest was successful because of the number of methods and submissions that we received for the tag. In this table, we show the participant methods, their acronyms, the input shape representation to solve the problem, whether the method uses deep learning or not, and finally a set of keywords to identify how this method works. There is an obvious predominance of deep learning methods applied on multi-view representations. We now briefly show the key ideas of each participant methods. For example, DNA is a method that computes image features from a pre-trained BGG network. The features are used to build a k-nearest network graph where a metric learning approach is conducted to find the dissimilarities between the 3D objects. Also, the normalized profile curve method assumes that objects are basically rotationally symmetric. The method proposes a characterization of the shape by its profile curve. Also, the Deep Representative Learning and Future Learning method, DRFL, uses a classic backbone to extract features from 3D models represented as point cloud. This method opts for deep inception blocks and multi-layer perceptrons to compose a deep neural network to get the features. There is also a method that explores the use of autoencoders architectures and metric learning to define a similarity between a pair of objects. The method proposes two variations of autoencoders, a typical autoencoder and variational autoencoders to compute embeddings for the input data. RingViewNet is a method that uses multiple sequences of images extracted from the top view of the objects And then subsequently, the sequence of images is treated as sequential pieces of data, which are fed into a recurrent network, coupled with an attention module to extract the features of the sequence, and also to extract the final features for an input object. The multi-view convolutional neural network on silhouettes, MVCNN, is a method that uses the silhouette representation of an object, which are fed into a pre-trained ResNet 18 network to compute learned features. So in these methods, basically the idea is to extract new information from the 3D shape in the form of a multi-view representation, and then the idea is to use classic neural networks for extracting the information from these multi-views. We have also some methods that basically takes some state-of-the-art approaches and applied these state-of-the-art approaches in our dataset. For example, MeshNN is a method that uses two algorithms, the MeshWalker and the MeshNet, in order to extract information from the three-dimensional meshes directly using the information as a graph. Also, the multi-view ResNet method uses the classical ResNet backbone to extract features from multi-view images. In this case, these multi-view images are basically the methodology of the multi-view CNN approach, but in this case using the ResNet 15 backbone as a neural network to extract the features. There is also a method, which is the PCI method, that computes only two views from an object. These two views are selected depending on the principal component analysis of the front and top view of the cultural heritage objects. So the idea is to extract only the two most relevant information from the objects, and then to use the convolutional neural network to extract the features from these two images. Finally, the 3D shape embedding method trains a joint method that classify and also autoencode the three-dimensional model using a multi-view representation, and the idea is to compute an embedding of 3D models and to use these 3D embeddings as features for compute the metrics of the similarities for our context. So our evaluation methodology consists of the participants submitted distance matrices between the test set and the training set. So basically the distance matrix contains all the distances between the objects in the test set against the objects in the training set. Thus, we compute the standard evaluation metrics such as nearest neighbor, first tire, second tire, mean average precision, normalized discounted cumulative gain, precision recall plus, and also confusion matrix. So let's see first what are the results of the retrieval by shape contest. Regarding the results and looking at the precision recall plot, 4 methods get high values of precision. It's worth noting that the method with the multi-view representations use 84, 12, and 10 views respectively, which is the case of RVN, TL, and MVCNN methods. On the other hand, MeshNN makes us to think that the connectivity information can be a good representation to test in the future. So probably we encourage to the community to explore this possibility in order to extract another kind of information about the connectivity of the objects. Also important, the RVN method uses a combination of RGB views, depth information, and silhouettes. So these findings suggest that the integration of different data sources enhances the characterization of our objects in our dataset. This table also shows the results and confirms that our previous claim that RVN, TL, and MeshNN are among the methods with the best performance. And this is because this method obtains the higher values in mean average precision and also in the normalized discounted gain metric. So in the case of the retrieval by culture, regarding this challenge, this precision recall plot shows that RVN and TL are again among the best methods. NVCNN obtains also a good performance, mainly at the first value of recall. We believe that the integration of color, shape, and depth information makes the RVN method an approach that takes advantage of multiple data sources to deal with the extraction of high-level features. Also in this table, we can see how RVN clearly outperforms the other method consistently in all the metrics. And we think that this is because the RVN method integrates many sources of information, and these sources of information contains a lot of information about the semantic notion of the culture in the dataset. So due to the invariant classes, we perform experiments in a class-by-class manner. So we compute the metrics within the classes, and then subsequently we average the class-based metrics. First, we note that the curves drop considerably. Also, in this experiment, we see that the MVCNN turns to be the best method, and it suggests that this method deals better with the amount of data in each class. This table confirms that MVCNN method outperforms the other method because we get all the higher values in the metrics in different runs of this method. We also show the precision recall plots for each class in the retrieval by culture challenge. Note how all the methods get high precision values with the most populated class, and this is because all the methods are obviously saturating the performance in the class that contains the large number of methods. However, we can see that most of the methods do not perform well in the class with the less populated number of objects. This is the culture 4. However, this is not the case for MVCNN, which is the only method that is able to learn from few examples. So, some important remarks are that in this competition, multi-view representation allows the learned features to characterize the objects with good results. However, we believe it's still possible to explore new representations and learning models. Some representations that we would like to test are point clouds, triangular meshes, and implicit representations. And now we have very good representative deep neural network methods to try with these new representations. As a last point, the semantic nature of the retrieval by culture challenge opens a lot of opportunities to search algorithms that extracts more semantic information from three-dimensional models. So I hope you enjoyed this presentation. Now we are open to questions and comments from the audience. Thank you very much. If you want to have the benchmark and all the information about the benchmark, you can visit our website, in which you can find the dataset, the ground truth, and the evaluation scripts available. And also you can contact me if you want more information about the dataset and the benchmark. Thank you very much.